Good morning, everyone. So today we're going to talk about efficiency in our work energy and power unit. Topic number 6, efficiency. So what is efficiency? So efficiency is a measurement of how much of the energy that you provide a machine is actually getting used. So for example, let's say we have a light bulb. So like this, don't know how to draw a light bulb, but so it uses electricity and it produces light, right, as an energy. So let's say the amount of energy that we put in, so we call it energy input. So let's say we put in a 100 joules of energy. So that's energy input. So how much energy are we actually getting out? So for example, how much energy is actually being turned into light in this case? So we call it energy output. So we have electricity input, and then we have some kind of light that comes out from the light bulb. So it's light output. Now, I think I've mentioned it in class, but incandescent light bulb, these really old light bulb that has a filament inside, is actually very inefficient. So at most, you're gonna get like 3 joules of light energy coming out. So efficiency is just a mathematical way of representing as a percentage how much energy input versus how much energy is being actually used output. So for example, in this case, we would say that the efficiency for this light bulb is 3%. So every 100 joules of energy goes in, 3 joules of it is actually being used to create light, and the other 97 joules of energy is wasted as friction, heat, all sort of stuff, right? So now let's write down the definition. So efficiency is a measure of how much of the energy, so how much of the energy that goes into a machine. So a machine could be a light bulb, it could be an actual machine, actually gets used. So how much of the energy that goes into the machine actually get used. So machines are useful because sometimes it allows us to use less force over a longer distance to do the same amount of work. So sometimes we use a machine. So for example, if you look at the to the right hand side, there's some examples. So for example, if you want to pick up a box, right? So like, and you move it upward, into the car. So you have to change the object's potential energy, right? So you want to move the box up, into the car. So you can pick it up from the ground directly, but that would require a huge amount of force. So sometimes we use an incline plate, and so incline plate basically let you spread out your work so that you can slide the box up, so you don't need as much force, but you will have to work for a longer distance. So the distance that you push, like from the ground to the back of the truck, is longer than the directly if you just put the box down there and directly pick it up. So that distance is longer, but you don't need as much force, right? So machines are useful in many ways. But the problem with any kind of machines, right, wheel and axles or screw or wrench, where basically a wrench is something that you make an axe with, so you can cut out so you can cut stuff with it, or lever or pulley system. But any kind of machine that you use, mechanical or electrical, is always going to be, well, imperfect, right? Just like a lot of things that we study in physics, we know that the world is usually imperfect. So there is actually a law that states that, any kind of machines, when energy is converted from one way to another, is called the laws of thermodynamics. Some energy will be converted into heat, right? So you're always going to lose energy due to heat. So what happened is, therefore, the amount of work that you input to a machine is always greater than the amount of work that you can get out. So that means you're always going to lose something, one way or the other. So the input of the work is the total energy supplied to a machine. So how much electricity are you putting in, or how much energy are you putting in to begin with for the machine to actually work? So the work output is the amount of energy actually used. So the amount of energy that the machine can actually use and actually make what you wanted to happen for you. So the equation for efficiency, though, however, is actually quite simple. So efficiency, so usually we have a shortcut. So we say efficiency, EFF. It can be either you can do it with energy. So it's the work output, which is the energy output, divided by the energy input, and you multiply by 100% so that you can get a percentage as your answer. Now remember, energy is measured in joules, right? Now this will always be less than 100% because no machines are perfect. So if you need to convert energy from one form to another, you're never going to get 100% of conversion. Now, however, you can also remember what power is, right? So power is how much energy is being used per second. So you can also use power. So you can do a power output over power input. So remember, power is measured in watts, which is the amount of energy in joules per second that the machine consumes. And you also make it into a percentage, and it's also less than 100%. So whichever way you do it is exactly the same. So you get the same answer no matter what. And the reason why is because power is just equal to work done over time, right? So when you think about it, so power out over power in is the same thing as work done out over time divided by work in over time, and the time will simply cancel out. So you get exactly the same equation again. So it's exactly the same thing. All right. Now, for efficiency, it's just a percentage of how much energy are you actually keeping, right, at the end. So there's no unit for it. So just write it as a percent. So like a 30%, 20%, something like that. Okay, so now let's look at the system. A lever is used to lift a 50 kilogram object 10 centimeters. To do this, we must apply a force of 75 Newton to the end of the lever, which displaces the object 1 meter. So now, when you want to lift something really heavy, so sometimes what we do is like that. So we use a lever system like this, and there's like a pivot point in here. So there's a plank that you can actually move. So you see people doing something like this with cars. Those hydraulic like jack that people use to lift up their cars to change the tires is very similar to this. So you have a long arm that you're going to push down. So from the side with long arm, so you're going to push down with a force of 75 Newton. And this side is like 1 meter to the ground. So 1 meter, 75 Newton. And on the other side is an object that's really heavy. So that's the 50 kilogram box. And it will go up. So by the time this goes down, so the box will go up to maybe like here. So let's draw like a picture. So what happened to the box is it will go like here, like this. Oops. Okay, you know how good Mr. John's drawings are. So let me do this again. So that's 50 kilogram. And so the box will only go up by a little. So the box will go to here. There you go. Okay, so the box will go to here. So the box only goes up by a little bit. So the box goes up by only 10 centimeters, which is 0.1 of a meter. Okay, so it's not to scale. Now, so on the left-hand side, you have the energy input on the left-hand side, because that's how much energy, well, that's the force that you apply to push it down, right? On the other side of that machine is the object being, well, actually going up. So that's the output. So the input and the output is over there. Okay, now let's calculate the change in energy on both sides. So on the left-hand side, where's the input? So we're gonna say what is your work done? What's your input work done? Well, work done can be calculated by force times distance. So you have an applied force, and that is 75 Newton. And you have a distance moving, which is 1 meter. So on that side, your total energy input is 75 joules. Okay. Now, on the right-hand side, what is happening? Well, on the right-hand side, you have a box that's actually going up. The box going up, that means the box is changing potential energy. So you can do work done is changing potential energy in this case. which is mgh. Now the mass and the gravity is not changing, so only the height is changing. So mgh, the height is changing by 0.1. So we can say the work output, therefore, is equal to mass of the box multiplied by gravity multiplied by the height, which in this case is 0.1 meter. So at the end, 49 joules in total. So 49 joules is the output. As you can see, the output is less than the input, right? So if you actually look at that, the output and the input energy. So output is always less than the input. Okay, so what is the efficiency of this machine, particular one? Well, that is not too difficult. So efficiency is just those two numbers. The output goes to the top and the input goes to the bottom, and then you times it by 100% so that you get a percentage. And if you use your calculator, you get 65%. Okay, so that's the efficiency of this particular machine. Okay, so hopefully it's not too difficult. Now I'm going to do one more example, which is on this page, question number 4. So now this one is a pretty classic one. So a 800, well, this is just 850 kilogram. So that's the way they have to write it. 850 kilograms, so that's question 4. I think that's question 4, yeah. Is pulled up at a constant velocity 1 meter per second by a 10 kilowatt motor. So 10 kilowatt, 10,000 watt. That's a power measurement motor. Okay, so calculate the efficiency of the motor. Now, so what do we do in here is so what's happening is there is an electrical motor. So the motor is like spinning and there is a thread attached to it so that it can lift up a mass, which is like a box, right? It's an elevator. So this is the 850 kilogram elevator being pulled up by the spinning of the motor. So this is the electrical motor on the top. Okay, so for a motor to actually, well, for a box to go up, the apply force, the amount of force that we need to apply to it, right? So let's say this blue free body diagram, apply force, must be at least, right? At least the force of gravity of the object, right? I mean, it can be more, but you know, at least you have to match the force of gravity of the object. Otherwise, the box won't even go up to begin with. Now, because the question said that this object is going at constant speed, so we know that for sure it must be exactly matching, right? So because it's constant speed, so constant speed means that, you know, we have to match it exactly. Okay, so the apply force, so we can calculate apply force, must equal to at least gravity, which in this case exactly gravity, which is mg. That's easy. So that's 850 multiplied by 9.8. So you can check it, but it's 8,330 Newton. Okay, so now, so that's the amount of force. So how much is what is the power output? So that means what can the machine actually do? Well, the machine is lifting up an elevator, right? So the elevator is lifted by a force, F, and we also have the speed that is going, which is V, Fv, right? This is the equation that's not on the formula sheet, but we talk about it on the last day's note. So power is, or can also be force times velocity if you have a constant velocity, right? So it's not on the formula sheet, but it works if you have constant velocity. And this time we do have constant velocity. So the applied force is 8,330 Newton, and the constant velocity is 1 meter a second. So that means the power output is 8,330 watts, right? Not joule. Typo. So 8,330 watt. That is the power output. Well, how much is the power input? Well, the question already gave you the power input. Power input is right here, 10,000. That's how much power the motor, electrical motor, actually needs in order to function. So that's called power input. And the power output is what can the motor actually do for you, which is lifting up this elevator. So it's 8,330 watts. So the efficiency, is power out. So it's always output over input. In this case, it's power output over power input. So power out over power in times 100%. So you can check my calculation, but I'm just going to write down the answer. It's about 83%. 83.3%. Okay, there we go. Now, so your homework is try the other 3 questions. And so in this case, let me move over there a little bit because I do believe that I forgot to include the answer key for this one. So I'm going to give you the answer right here. So question 1 is 56%. Question 2 is 48 seconds. I think question 2, yeah, 48 seconds. Question 2 might be a little bit harder. Question 3 is 43%. Okay. So now when you try this question, if you get it, of course, good. If you don't get it, as long as I see that you try, you still get any credit for it. And then, if there is any question, so for example, if a lot of people couldn't get like question 1 or question 2, I will have another video posting that I'm going to do this, so that you can actually look at how it's done. Okay, so as long as I see that you actually try, don't erase anything, and you take a picture, you upload it on the portal, just like what I instructed on the instruction page, that will be good enough. Okay, so that's it for this lesson. Right, short. The next one will be longer though. The next 2 will be longer. We actually just 2 days from finishing this entire chapter, so we're getting there. Okay, goodbye everyone. Bye.